Good morning, class. My name is Yanming Zhang. I'm going to be your new science teacher for this school year. Today, we are going to start with a topic that is related with physics or physical science. This topic is motion, okay? So let's think about this question. So what is motion and how do you describe the motion of an object? Have any volunteers? Okay, David, please go ahead. Okay. Okay, yes. Okay, that's fine. Pretty good. Yeah. It's very intuitive and straightforward. So motion is the change of a position of an object in an event, right? So then I'd like to know, well, is motion guaranteed? Do you always have motion, or is absolute, or is relative? Let's look at this example here. Now we are having a boy sitting in the car, right? And there is, in the background, there is a school, and there is a red car passing by. So now my question is, who is moving? Anyone? Okay, Lily, go ahead. Okay, okay, yes, okay. Oh, so Lily said the boy is stationary, he's not moving, and the red car is moving. How do you know? How do you know about that? Okay, Alex, go ahead. Okay, okay, very good. So Alex said that because in the background, the red car has moved relative to what? To the background of the school and to the car that is shown here, right? So the red car is moving, but the boy is stationary. Okay, that's a good point. That's a good point. So in reference of the background or the car in the front end, so the red car is moving, okay? But I would say the motion is relative, and it's relative to the reference point. So let me illustrate this. Suppose we have a cup sitting on the table, right? So is the cup moving? You may say no, because it's sitting on the table, it's not moving relative to the table, right? But this cup is also on the earth, right? This cup is also on the earth. So is the earth moving? Everybody knows that the earth is moving, is revolving around the sun, right? So if the earth is moving, so the car sitting on the table that's on the earth is also moving, right? So the motion is relative, and it depends on how do you select the reference point. And how do you select the reference point? You are going to select the point that is not moving, okay? That is having a simple motion, either not moving or a relatively simple motion. Okay, so motions are relative. Any questions about this? Okay, good. That's pretty intuitive and straightforward. Then let's look at another topic, which is distance and time. So why do we need to know the distance and time? Because this is how we what? This is how we describe the motion. Okay, that's how we describe about the motion. So because we care about motion in terms of how far we move in a certain amount of time, right? How far then is the distance, and how fast is the speed, right? And then we can do the measurement of the distance using the units. And this is called SIMI International, which is SI unit. So these are the conversions. 1 meter equals 10 decimeters equals 100 centimeters, right? 1 kilometers equals 1,000 meters equals 0.1 million of centimeters. Okay. Then we come back to the topic, that is how fast is the speed. How do we measure how fast? We are going to do what? Jacob, go ahead. How fast? How do you measure how fast? Okay, perfect. That's right. So we are going to measure how far object traveled within amount of time or a period of time. So speed equals distance over time, or v equals d over t. Then we have this issue here. So if you are traveling from Chicago to St. Louis, are you going to move at the same speed all the time? No, probably not, right? So then we are wondering, on average, or typically, how fast did we move, right? Then how do we do that? How do we calculate the average speed? Go ahead, David. Yes, yes. Okay, good. Yeah, so David said, you need to do what? You need to know what's the distance you traveled overall, and then to divide what? The time you have used during that time. That's perfect. So average is total distance over total time. So that's basically the overall slope. Yeah. And how about the instantaneous speed? What is the instantaneous speed? Alex. Yeah. Good. Yeah, that's right. So instantaneous speed means the speed at a given moment. So it's basically the slope of the tangent line on the curve at a given point of time, right? So the slope is actually rise over run by definition. So if we look at the dt diagram, this is d over t. So d is what? Right. D is x and d is y, which is dependent variable, and t is x, which is an independent variable. So then we have what? We have three stages here, 1, 2, 3. And can anyone describe what's happening here in stages 1, 2, 3? Go ahead. Okay, so yeah. So John said, in stage 1, it is what? It is uniformal motion, which means you do not have the speed change, right? And has a uniformal speed, right? And then in stage 2, it is standing still because you have zero change of the distance in stage 2. It's stationary. And in stage 3, it's moved again. So let me know, please, which stage it is moving faster, stage 1 or stage 3? Jacob, go ahead. Okay, that's right. Jacob said stage 1 moved faster. Why? Oh, because the slope of that line is steeper than the slope of this line in stage 3. So stage 1 moved faster than stage 3, right? Very good. Because V equals D over T, right? Now let's do some review and assessment. Number 1, what is the SI unit of distance? A, foot, B, meter, C, mile, and D, kilometer. Which one? Okay, that's meter. That's right. Thank you, Lily. Thank you. Okay, next one. A change in position with respect to a reference point is called what? Okay, that's called relative motion or motion, simply. 3. Suppose you are in a train. List some objects that make good reference points to determine whether or not the train is moving. Okay. So we could have what? We could have stationary items like the rail of the road or the houses on two sides. Like that. Right. So these are the answers here. Let's move on to the next one. Unit conversion. 1 meter is equals to what? 100 centimeters? Good. Thank you, John. So 1 meter also equals Jacob? 10 decimeters. Thank you. So 1 meter is also equals, Livy, go ahead. Yes, 1,000 milliliters. And 1 kilometer equals, yes, 1,000 meters. Any questions about this? Okay, fine. Let's move on to this question. 4. Compare and contrast. Suppose you are standing on the sidewalk. Describe the direction of your motion relative to the car and the plane. So you are standing here. So according to the car and the plane, you are moving what? To the right side. But according to the trees, the shrub, and the house, and the bushes, you are what? You are standing still, right? So like that. Very good. Next one. Compare and contrast. Suppose you are riding in a plane. Describe the direction of your motion relative to the person standing on the sidewalk and the car. So you are in this plane now. You are moving relatively to the person. You are moving to the, yes, right, to the left. So according to the car, you are also moving to the left. Okay. We have more review and assessment. Okay. Speed and velocity. What quantity can you calculate if you know that a car travels 30 kilometers in 20 minutes? So John, 30 kilometers means what? Okay, that's right, it's distance. And how about 20 minutes? That is denoting what? Jacob? Yes, time. So how do you calculate, how do you combine distance and time? Use the formula we used. This time is speed, right? So then which one can we calculate now? Average speed. On the graph of distance versus time, the slope of the line indicates the speed of an object. Okay, that's good. Last one here. The graph shows the motion of a remote control car that is doing like this. So during which time period was the car moving fastest? So fastest what? Fastest means it has the what? Yeah, correct. The largest speed. And then how do you find out the largest speed? Because the speed is what? Yes, the slope of the line. The slope of the line is speed. So in order to find the fastest moving car, period, we are going to find the largest speed. And in order to find the largest speed, we are going to find the steepest slope. And which one is the steepest slope? This one. How do you know? Because you do calculation. 4 over 4 is actually 1. And you do this. 2, the rise over run, the rise is 2 here, and the run is 4. 2 over 4 is actually half, 0.5. So this one have a speed of what? 0.5 units, 0.5 meters per second. And this part has 1 meter per second. So which one is faster? This one. What was the speed of the car during the first 4 seconds? So we calculated that's 4 over 4, so that's 1 meters per second. And how about in between 4 and 8? It did not have a rise, but have a run of 4. So the rise is 0, and 4 is the run is 4. So 0 over 4 is 0, right? So it didn't move at all? No, it did not move in between 4 seconds and 8 seconds. Okay, good. That's very good. So we practiced one thing here. So let's switch to another topic since we have time. So let's say Newton's law of motion. Physics, Newton's 3 laws of motion. Sample lesson for KIPP interview. Background about Newton. So Newton discovered the 3 laws of motion. So everybody knows that Isaac Newton was born, was a famous scientist. So he was born in 1643. His family was wealthy, but he had so that he had some advantages of the other kids because he had received good education, but also that he did not have a good childhood because his father died right before Isaac was born. So he was raised by his grandma and relatives. So he did not have a father. So at first, he was not to learn much. He was not learning too much in school, and he didn't pay attention to school, and was so-called very lazy. So later on, his uncle prepared him to go to college, and then he started being showing interest in school and developed his. One of the skills he has developed was making model machines, including clocks and windmills. In college, he began to study the latest theories in math. Soon he was coming up with theory of his own, and today Sir Isaac Newton is well known for his 3 laws of motion, as well as other scientific breakthroughs, such like inventing the calculus. So here are the Sir Isaac Newton's 3 laws of motion. First is the law of inertia. The second is the law of acceleration. And third law is the law of action. As you can see, it happened to be that this son was spelled the first name of Newton, Sir Newton, as Isaac. So the first law is the law of inertia. The first law denotes that an object moving in a straight line will continue to move in a straight line unless acted on by an outside force. Also, as an object at rest will stay at rest unless acted on by an outside force. This is the word form of. So the formula format of this law is actually when the F net is 0, the velocity is either 0 or the velocity is a constant, which means you are having a constant magnitude and direction. So then we have to define what is inertia. Inertia is a reluctance to move. Suppose you are pushing a box. The larger the box, the harder you are going to get it to move. Okay. So more mass, more inertia. The heavier the box, the larger mass the box, the more inertia it has. The second law is the law of acceleration. Force will cause a change in the motion of an object. The change in motion depends on the amount of force and the mass of the object. The formula denoted here will be F net equals m times a. M is mass and a is the acceleration. Okay? It means with a larger force I'm putting, the object is going to change in speed. with a larger magnitude. Third law of motion is the law of action-reaction. Any one force will be accompanied by a force the same with the magnitude but opposite in direction. This is called action-reaction pair. Formula represents F equals negative F1 equals F action equals F negative reaction. Let's use the three laws of motion and the free body diagram to analyze the box sitting on the ground. Okay, so what do we have here? So we have a box sitting on the ground. So first of all, on the Earth, you are guaranteed to have one. You are guaranteed to have a gravity, right? You're guaranteed to have a gravity. Let me add this on here. Then what does the ground do to the box? It is supporting it, right? So the box have the ground is having a support force having a supporting force to the box. Let's say by definition is called the normal force. So will the normal force opposite and get the gravity balanced? Yes. So now what? Now F net is 0. So this, which law could be applied here? Which law could be applied here? Yes. That's the first law of motion, the law of inertia. Basically, the net force is 0 here. So, is a box moving? In this case, it's not moving. But in case it's moving, it should move in a constant velocity and a constant velocity, which means constant, no changing magnitude and no changing of directions. Let's do it this way. Let's say now you're pushing this box. Okay, you're pushing this box. Okay, you're pushing it to the left. And in case I'll say your push is not enough, and it is not still moving. So how could this happen? How could if you push and it is not moving? Why? Because of what? Yes, that's right. Thank you. Because there's a what? There's a friction force countering it, right? There's a friction force countering it. To which direction? Yes, to the right. Okay, this is friction. So now, which law could be applied here? Which law could be applied here? Yes, still the first law of motion, the law of inertia, right? Because what? The net force is still 0. Let's look at this situation here. So what if this is the ice? You have no friction. What happens? Now the box starts what? Not only moving, but also accelerating. It is moving faster and faster and faster, just like your naughty brother is pushing a cart on the parking lot of supermarket, right? So he's pushing it. It's going faster and faster and faster, right? Yeah. So then which law is applied here? Obviously, the net force is not 0, so the second law applies. F net equals ma, right? So we can calculate actually how fast it is accelerating, right? And now, let me give you a very tricky question here. Okay, so we are going to use a third law. If we have a gravitational force here, and we are having a normal force here, these forces are what? Are the same in magnitude and different opposite in directions. So are they an action-reaction pair? That's very tricky, right? The answer is what? Yes or no? Who voted yes? Raise your hand. Okay, 3 of you. So who would know? Okay, 2 of you. Okay, good. So actually, you know what? This is not an action-reaction pair, because for action-reaction pair, you are going to switch the givers and the receivers, right? Let's analyze this. Okay? Let me draw a table, hopefully. Let's say giver and receiver, okay? The giver is and the receiver is a box. And Fn, the giver is the surface of the Earth. And the receiver is the box, right? If we want to do the reaction of Fg, that should be what? You should switch the box, should switch the giver and receiver here, right? You switch that and you switch that, right? Let me color code this really quick. Here is green and the box is red. Yeah, you're switching this, right? So box is giving some force to the earth. That's what? That's actually what? That is actually the pressing down force from the box, right? Is that pretty cool? Actually, the normal force and gravity of the box, they are not action reaction pairs of the gravity of the box. Actually, the reaction force will be the attractive force from the box to the Earth. Is that clear? Okay, good job today. That's counted our lesson today. If you have any questions, just email me or call me later, or submit a ticket online so that I can answer more questions. Please do the homework in the textbook, chapter 5 and chapter 1 too. For more details information, please look on the online Blackboard. Okay, have a good one here. So happy Memorial Day. Oh, that gave me Aspen Island sign. Sorry, I submitted this video. I got delayed. But anyway, this is within 5 business days because it's just 5 business days. Actually, I have one more day because Memorial Day is also a break, so it's not a working weekday. Anyway, I submitted this video early. Hopefully, that will come like that. And thank you for giving me such an opportunity to interview with KIPP. I really like to, I'm looking forward to getting more responses or interact more with you in the near future. Thank you, and have a nice holiday. Have a good one, and see you later. Thank you. Bye.